In this video, I'll demonstrate how to use logarithmic differentiation to take the derivative of some more complicated functions. So our directions are to use logarithmic differentiation to find dy dx of the following. And the first function is y equals 3x plus 5 all to the fourth power all over 20x. And certainly we could use the quotient rule, but I'm going to use logarithmic differentiation. And the first thing you need to know is that if you take the first derivative, this d dx of the natural log of u, that equals, remember that the first derivative of the natural log of something equals 1 over u. And now because of chain rule, we have to say, well, what is the derivative of the inside there? So I'm just going to shorthand that and say that's times du dx. That's not really shorthand, that's the way to write that. So that means the chain rule. Derivative of the outside times the derivative of whatever this u function is. And we're going to have a lot in the u here in this one. Okay, so I'm going to begin by taking the natural log of each side. So even though the y, because you have to do the same thing to each side. So I'll write natural log of y equals the natural log of this big thing, this 3x plus 5 all to the fourth power over 20x. Natural log of all of that. Now I'm going to simplify each side. The left-hand side doesn't require any more simplification, so I'll just write natural log of y. And here, if you take the natural log of a quotient, it's the difference of the natural logs of each of those. So I'll write the natural log of 3x plus 5 all to the fourth minus the natural log of 20x. So that's the first step. Now we could take this 4, this exponent of 4, and move it to the front. Move it is not a mathematical term, but we can think of it like that. That's what's visually happening. So I'll say the natural log of y equals 4 times the natural log of 3x plus 5 minus the natural log of 20x. At this point, I'm going to take the derivative of each side. And I'm going to use some implicit differentiation. So the derivative of natural log of y is 1 over y multiplied by the derivative of y, and that is dy dx. And that's what we're going to be going for. So we're going to be simplifying or getting dy dx by itself. So again, this was implicit differentiation. And I'm just going to write a little note here so that you can see that later. Okay, that was implicit differentiation. Equals, the 4 just tags along, 4 times 1 over, here's what we're going to do, 1 over the u, that's 3x plus 5. So just to make a little note of what we've done up here, this is our u multiplied by the du dx, so the derivative of 3x plus 5, and that's just 3. So I'll write that as a note also. This is the du dx. And I'm going to do the same thing over here with the minus natural log of 20x. I won't put the notes in the blue. So minus 1 over u, or the 20x, multiplied by the derivative of what's inside there. So the derivative of 20x is just 20. All right, let's clean this up real quickly. I'm going to do a lot in this one step. I'm going to multiply each side by y so that I have dy dx by itself. So dy dx equals, I have y times 3 times 4 is 12, so I've got 12 over 3x plus 5. And this is still in parentheses, minus 20 over 20x, so the 20's cancel and we have 1 over x. And the last step, if you wish to do it, is to substitute back in for this y. And that initial y was this. So we'd plug all of that back in. So for the last answer, I'll use a different color. I'll say dy dx, or y prime if you like to write it a little bit shorter. Dy dx equals the 3x plus 5 all to the 4th power over 20x minus times 12 over 3x plus 5 minus 1 over x. And you may wish to clean that up more, but for now I just want to show that structure or the process of the logarithmic differentiation. All right, the next one, let's see if you can play along here. We're going to take the natural log of each side, and we'll do that, and I'm going to say the natural log of y squared equals the natural log. I'm going to go ahead and skip a step here. I'm going to take the natural log of this whole thing, and the natural log of a product is the same as the sum of two different natural logs, right? So I'm going to say the natural log of 3x minus 2 to the 1/3 plus the natural log of x squared plus x to the 5th. All right, now let's get to it. So I just skipped that step of writing natural log of that. Okay, we can move this 2 over, so we've got 2 times the natural log of y equals 1/3. I'm taking this 1/3, moving it. 1/3 times the natural log of 3x minus 2 plus 5 times the natural log of x squared plus x. I'm going to have to start writing a little bit smaller so I can so I don't run out of room. At this point, I'm going to take the derivative of each side. I'm going to use implicit over here again. I've got this 2 just tagging along, so 2 times 1 over y, or 2 over y, multiplied by the derivative of y, and that's just dy dx, equals 1/3 tags along, multiplied by 1 over 3x minus 2, multiplied by the derivative of 3x minus 2, which is just 3. I'm going to put this in parentheses so I don't get that mixed up, plus 5 times 1 over x squared plus x times the derivative of x squared plus x, which is 2x plus 1. Right on the edge there. All right, moving on. Let's kind of cut to the chase here. I've got dy dx, and I'll write that dy dx, and then multiplying by y over 2 to get dy dx by itself. So I've got y over 2 multiplied by all of this stuff that I have here. So the 3's cancel. That's kind of nice right here. These 3's cancel. So back to it. I've got 1 over 3x minus 2 plus, nothing cancels here. I'm going to distribute this 5. I'm going to distribute this 5 times the 2x and the 1, because I could just move this commutative property of multiplication. I could say 5 is being multiplied over here now, and that's fine. I'm not breaking any rules or changing the value of the problem. So I've got 10x. Let's put that all in the same color. I've got 10x plus 5 over this x squared plus x. At this point, you certainly could choose to simplify this some more. You could take the square root here and say positive or negative, and plug in for y here. But again, I'm just showing the process of using logarithmic differentiation to find a dy and dx of some larger, messier problems.